So this is going to be a short review for the exam coming up, chapters 5 through 8. So I'm going to do some example problems, maybe even some from the practice exam, just to give everyone an opportunity to get in on a review if they can't make some of the review times. The exam is 36 questions. 34 of those are worth 100 points, and the last 2 questions are going to be extra credit questions. All right, so let's start with some chapter 5 examples. So this first problem here is from chapter 5. It has the temperature outside at 302 Kelvin with car tires that have a pressure of 1.1 atm. It's then asking what the pressure is going to be if the temperature decreases down to 273 Kelvin. And then it's also telling us that the volume is going to remain constant. So with these chapter 5 problems, there's a lot of equations to choose from. So sometimes it's best to just go ahead and write a list of what you have, your knowns and unknowns, so that it makes it easier to figure out what equation you need to be using to solve the problem. So I'm going to start with this 302 Kelvin. That is a temperature. I'm going to call that my TI, my initial. And then at 302, the car tire pressures are at 1 atm. So the pressure that belongs at that temperature is 1.10 atm. It's then asking, what would be the pressure if the temperature decreased, and I'm saying decreased because it went from 302 down to 273. So that second temperature I'm going to call TF. And then PF is what we're looking for. So what pressure? So that's why I put PF with a question mark. So now if we are looking at all of our equations in chapter 5, the only equation that has both pressure and temperature is going to be that combined gas law, which is that PI VI over TI is equal to PF VF over TF. Okay, so for this combined gas law, notice we have volume in it as well, but they didn't give us any actual values for volume. However, they did say the volume remains constant. Okay, so if the volume is going to remain constant, that means we can take it out of the equation. Why? Because it's constant. It's the same on both sides, so they cancel each other out. If volume was 1 on the initial, it would be 1 on the final. 1 and 1, cancel. If it was 2, and then 2 over here, 2 on both sides of the equation are going to cancel. Okay, so that's why we can just cross them out. So this makes our equation now just have pressure and temperature in it, which is what we need because those are the variables given to us. So the new equation is just going to be PI over TI is equal to PF over TF. Now we're solving for the final pressure. So we want final pressure by itself. We need to get rid of this TF. Since it's in the denominator, we need to multiply by TF so that they're on opposite sides of that horizontal line and they cancel. So on this side, they'll cancel. Whatever we do to one side of the equation, we have to do to the other. So I'm going to multiply this side of the equation by TF as well. Let me erase this so we're not getting those mixed together. Okay, so now my newly rearranged equation has PF by itself. And then the other side of the equation will have final temperature multiplied by initial pressure. And all of that will be divided by the initial temp. Once I have my equation rearranged, I can plug in my variables and solve. So let's plug in final temperature, which is 273. For pressure, 1.1. Initial temperature, 302. So some things to point out before we calculate this is make sure you are putting the right numbers in the right places. So really look, did I put the initial temperature in the denominator and not up here? Also, I didn't mention this, but make sure your units are correct. Okay, so both my temperatures in Kelvin, my pressure in ATM. Okay, basically as long as the units are the same, so as long as both temperatures are in Kelvin, you're fine. They're both in Celsius, that would be fine too. Just make sure they're consistent with each other. All right, so let's solve. 273 times 1.1 divided by 302. Now, I would expect that my pressure would go down, and it does. Okay, but let's discuss that concept for a minute, because this exam isn't just about calculations, it's also about concepts. So when I get my answer, it's 0.994 ATM. So the pressure did go down. It went down from 1.1 down to 0.994. Okay, how did I know, or how did I predict it would go down though? I predicted that because of the temperature went down. So if the temperature here is decreasing and that volume's kept constant, the temperature goes down, what's happening to those molecules in the tire is they're slowing down. They're not moving as fast. When it gets colder, the molecules don't move as fast. When they don't move as fast, what happens is they're not applying that much force to the inside of the container they're in, to the tire. If they're not applying a lot of force, then the pressure is going to go down. So we need to know the definition of pressure. It's dependent upon force and area to be able to make that prediction. So just be aware, you need to know the concepts as well, so you might want to have a copy of the PowerPoints out or some notes that you have taken to refer to for the concept questions. Okay, some are calculations, but some are concept. I just want to point that out. So let's look at this next problem. And it is calculate the volume of 1.75 moles at STP. All right. So, another chapter 5 problem. We need to look at what information we have, and that will help us pick out the problem. So we have 1.75 moles. So that variable is n. So moles belongs with the variable n. Okay. Volume is what it wants us to calculate, so I'm going to put volume with a question mark. I obviously need more information than that, and that's what this STP is for. Remember, STP is standard temperature pressure. So whenever you are given STP, it's telling you that the temperature is 273 Kelvin, because that is standard temperature. It is telling you that the pressure is 1 ATM, because that is standard pressure. So looking at all the equations, the only equation that has all of these variables in it and only one of each variable is the ideal gas law. So with this ideal gas law, I need to rearrange it to solve for volume, because that's what I'm trying to solve for. That's where my question mark is. So I need to get rid of the P. To do that, I'm going to divide both sides of the equation by P. That's going to cancel it out. On the left side of the equation, I'm going to get volume by itself. So my equation becomes nRT over P. All right, well, when you go to solve it, right, you know what n is. That's 1.75. And you're supposed to multiply that n, that number of moles, by R. Well, notice they didn't give us R in the problem. But that's okay, because R is a constant that's given to you on the equation sheet right underneath this equation, because the R is always going to be the same in this class. That R value is 0.08206. So we're going to plug that number in for the R value. We're then going to take our standard temperature of 273 and plug that in for temperature. And then standard pressure is just 1. I get 39.2 liters, 3 sig figs, right? Let me plug that in over here. 39.2 liters. All right. So let's look at another problem. So we're going to do one more from chapter 5, and then we'll move on to chapter 6. So we have say 1.00 grams of O2 taking up a space with volume 0.250 liters at say 290 Kelvin. Kind of making things up as I go along. You know how well that works for me, right? So let's say, what is the pressure? So this is one of the harder problems, mainly because there's going to be some conversions needed. So we have 1 gram of O2, we have a volume, we have a temperature, and they're asking for pressure. So I'm going to start by making my list because it just helps me keep track of things and then realize where I need to go from there. So 1 gram, what is that? Okay, that's a mass. Volume, 0.250 liters. 290 K is a temperature. And then pressure is what they're asking for. Okay, well, it's chapter 5 problem. I have pressure, temperature, volume. I only have one of each. So the only equation that I'm seeing here that could apply, once again, is that ideal gas law. Okay, so I'm going to add my R over here because I know what that is. When it's the ideal gas law, it's always the same. So let's see what I have. Do I have pressure? I don't, but the question's asking for pressure, so that's what I'm trying to solve for. Do I have volume? I do, so check on that. Do I have moles? I do not, so no check on that. I'm going to erase that. R value I have, T I have. Okay, so in order to solve for this, I need all variables, right? One unknown, which is pressure, and then I need to know the rest of them. I don't know what my moles are, but I know my mass. So can we somehow take the mass of something and figure out the molar amount? In chapter 4 we can. We did it in chapter 4. And finals are coming up, so we might as well bring it all together now because we're going to need it all in a week anyway. So we can. So my first step, I need that N value, so I'm going to convert that 1 gram to moles. So how do I convert from grams to moles? Remember, molar mass, because remember the units on molar mass are grams per mole. So I need to calculate the molar mass of that O2 molecule. So oxygen, how many atoms of each? 2. Molar mass, 16. So this 2 is coming from the subscript after oxygen. This 16 is coming from the periodic table because oxygen has a mass of 16. So my molar mass is 32 grams per mole. So this is my conversion factor that I'm going to use to convert that gram amount to a mole amount. So now let's write my railroad tracks, because I have my conversion factor and I'm ready to do this conversion. I'm going to start with what was given in the problem, the 1 gram, because that's what I'm trying to get rid of. So I'm going to take this conversion factor, and do I want grams on top or bottom? I want them on bottom so they cancel. It's going to put my 1 mole on the top. So 1 divided by 32 gives me 0.03125. And this is moles. So I now have moles of O2. And they want to know the pressure of O2. So that's the moles that I need to use in this equation. So I'm going to write that over here under N. So it's all in the same place. All right. So I have everything I need. Let's rearrange. So what am I solving for? So I look for where the question mark is. I'm solving for pressure. So I want pressure by itself. So I need to get rid of volume. So I'm going to divide by volume. Whatever I do to one side, I'm going to do the other side of the equation. Volume cancels out here. I have pressure by itself. My equation becomes moles times gas constant times temperature divided by volume. Now let's plug in the numbers for the variables and calculate. My molar amount was 0.03125. My R value is 0.08206. My temperature is 290 Kelvin. And my volume was 0.250 liters. Now I want to take note here that I need to have liters for this problem. So the ideal gas volume has to be in liters, temperature has to be in Kelvin. Okay, so just be aware of that. They already were, so I didn't need to do any conversions. All right, so take my molar amount times my R value, times 290, by 0.25. And I get, after all that work, a pressure of, how many sig figs are we looking at? Just the 2 from here. So it's 2.97, so it would round up to 3.0 ATM. Excuse me. All right. Let's put another one. Moving on to chapter 6. So I'm going to calculate molarity. So you remember in chapter 6, it was all about concentrations. We talked about the definition of a solution, which was solute plus solvent. So a solution is made up of 2 different parts. And we also talked about many different types and ways to calculate concentration. So just grabbing my periodic table here because I'm going to need it for this one. So for this specific question, we're trying to calculate molarity. So the nice thing about the chapter 6 equations is you don't have to guess to what equation you're going to use. There's several to choose from, but the problem itself tells you which one you'll be using. So molarity is mole of solute over liters of solution. So once you know this, the next step is just to figure out the information given, how to get moles of solute out of it, and how to get liters of solution. Sometimes they're already in the correct units, most of the time they're not, okay? And I want to point out, I am showing the harder problems. Not all of them are going to be this intensive. So let's look. We have 2.33 grams of KCl, sorry. All right, well, is that moles? No. So we need to get that in moles. So that's going to be one step we need to do to solve, is to get this grams of KCl into moles. Okay. Now the next piece of information is 250 milliliters of solution. Well, looking at the equation, I don't need milliliters of solution, I need liters of solution. So I'm also going to have to convert the milliliters to liters. So let's start by doing this first step. Let's get our moles first, because that's going to be the more intensive one. So we're going between grams and moles, much like on the last problem. If you go between grams and moles, which piece of information do you need? Molar mass. So we have potassium, we have chlorine. I find those on my periodic table. I have one atom of each according to my chemical formula. Potassium is 39. Chlorine is 35.45. So my total molar mass, I'm going to add 39 plus 35.45. And I get 74.45, running out of room, grams per mole. So this is my conversion factor that I'm going to use to get 2 moles. So I'll write CF above it, my conversion factor. So once I have my conversion factor, I can do my railroad tracks. What's going to go in this upper left-hand corner? What we're starting with, the grams. Okay, so I'm going to put my 2.33 grams starting. Then I will take my conversion factor, and I just need to figure out how it goes. Do I want grams on top or grams on bottom? Since I want to cancel out grams, I'm going to put it on the bottom, so they're on opposite sides of that horizontal line, putting my moles on top. This is going to cancel my grams out. When I do that division, I get 0.031296. There's a lot of numbers. Okay, so this is moles. So this is going to be my moles of solute that's going to go in the numerator. So I'm going to write that in right now, just so I have it started. And you can use all the digits, or you can round. These numbers are going to be far enough apart that you'll be able to choose the closest correct answer. Okay, so if you round, you might get slightly different, but not different enough to not realize what the answer will be in a multiple choice. All right. We still need our liters of solution, so that's where this step 2 is going to come into play. It is metric to metric because we see LL, liters, liters, so we can use that KHD space DCM. Well, what's going to go in our empty space? We're talking volume, so it's going to be an L for liters. We're at milliliters. We're at the little m. We want to get to the L. So we're going to move that decimal point 1, 2, 3 times to the left. There is no decimal point present in this number, so where do I start? I'm going to start at the end of the number, and we're going to move it 3 times to the left. 1, 2, 3. So my new decimal point is right before that 2, giving me 0.25 liters of solution. So this amount is what I'm going to plug in the denominator of my molarity equation. Oh, and I just erased my molar amount. I guess I'll have to round. Divided by 0.25. So the molarity of this solution is 0. And we're looking at 2 sig figs, so 1,3, and then units are just capital M for molarity. You can also put moles per liter. They're the same thing, because moles of solute divided by liters of solution gives me the units moles per liter. So this would be probably the hardest type of concentration molarity problem that you will see. Okay, so let's continue on. Still in chapter 6, so we're still going to look at a few more concentration problems. We're going to look at what is the ppm composition of a contaminant, well, you know what I'm saying, found in groundwater consists of 2.27 grams per 550 kilograms sample. ppm means part per million. Okay, so nice thing once again about the concentration is they tell you what equation you're using. We're using the parts per million equation. Parts per million equation is grams of solute over grams of solution times 10 to the 6th, or times a million. That's why it's called parts per million. All right, so to solve this problem, we need to figure out what's the solute and what's the solution. So solution is made up of solute and solvent, the solute being in lesser amount, the solvent being in greater amount. Okay, well, what's the smaller number here? 2.27, so that's going to be my solute. So my solute. So is it in grams? Like it says here, it is. So let's plug that in. 2.27 grams. Okay, now on the bottom I need grams of solution. So the other number given to me is 550. Okay, first of all, I'm noticing two things. One is this 550 is of the sample as a whole. So that means it's the contaminant and the groundwater. So that is my total solution. So this value here, this 550, is representing the solution as a whole. The other thing though that I'm noticing is that looking at the parts per million equation, it wants the solution in grams. What is the solution in the question? It's in kilograms. Okay, so I need to convert that 550 kilograms to grams before I can throw it in the denominator here. Okay, so to do that, I'm still going to use that KHD space DCM, except for this time I'm talking about mass, whereas last time I was talking about volume. So what's going to go in that empty space? Be a G for grams. Okay, and I need to move the decimal point how many times? Let's see here. I'm at the K, and I want to get to the G. So I'm moving it 1, 2, 3 times. But this time, notice I'm moving to the right. And this number doesn't have a decimal point, but we're still going to start at the end of the number like we did last time, except for we're moving 3 times to the right, which is going to cause us to have 3 empty spots. I'm going to put zeros to fill in those 3 empty spots. That's going to make my gram amount, so 550 kilograms is going to equal to 550,000 grams. So that's the amount that I want to plug in down here so that my grams cancel. I'm going to multiply that then by 10 to the 6th. Don't forget that last step. It's called parts per million because we're multiplying it by 10 to the 6th, a million. So calculating this out, oh, of course I entered it wrong. Here we go. 2 sig figs, so 4.1 parts per million. All right. So I think there's one more I want to do in chapter 6. Might be 2. Once again, I'm showing the hardest ones. So there are 34 problems, and I may be showing like the 6th hardest that you'll see. So the rest are going to be not as in-depth. So now let's look at how many grams of KBr are needed to make 250 milliliters of a 1.8 solution. And I have done one like this on a previous video, but I just wanted to kind of bring it back to the review. Alright, so for this one, it's mass volume. So I'm going to get that equation written down. I have percent mass volume is equal to my, almost wrote moles, grams of solute over milliliters of solution. And then since it's a percent, I'm going to multiply that by 100. All right, so this one's hard because it's a rearrangement. Okay, so you can either plug in the numbers and then rearrange it, or you can rearrange it first. On ones like this, I prefer to plug in the numbers, but it's your choice. So what do I mean by plug in the numbers? I mean, I'm going to take this 1.8% and I'm going to plug it in where this percent sign is. So I have 1.8 here. Grams of KBr, that's what it wants to know. So I'm going to call this my X. So that grams of solute in the numerator there, that's the X that I'm trying to solve for. Okay. On the bottom is milliliters of solution. They gave that to us, 250. And then don't forget about that 100. All right, to make my life easier, what I'm going to do next is I'm going to do this calculation. So I'm going to take 100 divided by 250. So I only have one number to deal with on this side. So 100 divided by 250. And I get 0.4. So that gives me 0.4, sorry, X. So I just took 100 divided by 250 so that I just have one number here instead of the 2. So I get 0.4x. So now if I want x by itself, what do I need? Divide both sides by 0.4. So x is going to equal 0.4 cancels on that side. On the other side, to get x, I take 1.8 divided by 0.4. And I get 4.5. Now what was x again? Grams of KBr. All right, and on these ones, when you rearrange, especially this type with all the words and craziness, it's nice sometimes to just calculate it using the grams you calculated to make sure the percent matches up. So I'm going to do that quickly. So if I want to figure out the percent, I'm going to take the grams, 4.5, I'm going to divide it by the milliliters, 250 times 100. 4.5 divided by 250 times 100 equals 1.8%. So, does it match? It does. So this is the correct answer. Just a nice way to kind of double check your work there. All right. Continuing on, let's do a 3.5 milliliters of 2 molar solution diluted to 10 milliliters what is the concentration? So this is still chapter 6. And this time what we're looking at, dilution. Okay, another reason I can guess that is I have 2 volumes and I'm going to have 2 molarities. One here and the other is for the concentration. So a dilution equation is that M1V1 is equal to M2V2. The nice thing about this equation is you don't have to convert the milliliters to liters as long as they're the same units. What that means is as long as volume is both in milliliters, you can leave it. If it's both in liters, you can leave it. If one's in milliliters and the other one's in liters, that's when you have problems. So for now, it's good. Both are in milliliters, we don't have to do any conversions. Okay, we just need to figure out who belongs with who. So this 2 molar solution, I'm going to call that M1. How much of that 2 molar solution is there? 3.5 milliliters. So that's going to be my V1. So going to this next value, the 10 milliliters, that's going to be my new volume, or my V2. And what we're trying to figure out is what is M2? What is my new concentration going to be? Okay, so I'm going to plug in these numbers to solve. So we're trying to solve for M2, and we have 3 of the other 4 variables. So I'm rearranging this to solve for M2. So to do that, I'm going to divide both sides by M2, which will get me V2 is equal to M1 V1 divided by M2. So plugging in, M1 is 2, V1 is 3.5, and I realized I just made a mistake. What happens when you go too fast? Look at that. I divided by the wrong thing. I solved for V2, and I don't need to solve for V2, I need to solve for M2. So what I should have done was divide by V2 on both sides to cancel out V2. That way M2, I'm still multiplying those 2 on top, M1, V1, but I'm dividing by V2, the 10 mils. So don't go too fast, and if you see a mistake, stop, go back and correct it. You just saw, I make mistakes too. Okay, so the new concentration, my M1, is going to be 0.7 molar. And it makes sense that the molarity decreased because I added more water. I have more volume. So by adding more water, you're diluting that 2 molar down to a lower concentration. All right, I just have a few more that I'm going to go over, and that'll be it for this review. If you have any other questions, though, we can always meet up via email or via Zoom, whatever works. I wanted to do one of these because I explained it on the PowerPoint, but I don't think I ever actually did one in a video. So I just wanted to show one of those. So equivalence per liter. So we talked about this in the PowerPoints, and to figure this out, this is not an equation you have. You need to take the concentration, so the molarity, times the magnitude of the charge. So what does that mean? Well, the concentration, the molarity, that part's easy. That's the 0.75. But the magnitude of the charge, what this means, this is the ion. So you're always going to be given an ion. They'll tell you what the charge is. So this particular ion, its charge is 3 minus, or minus 3. Now the reason I say magnitude of the charge is because you'll never get a negative equivalence per liter. So I want to take the number 3 down, but I don't want to bring the negative sign with it. I want to take my concentration, 0.75, and multiply it by the number 3 without the charge. So my equivalence per liter is going to be 2.3 if we're doing sig figs. So those ones aren't particularly difficult. The only problem with them is you're not given an equation, so when you see it, you have to remember, oh yeah, I'm taking the concentration and I'm multiplying it by the numerical value of the charge without the actual sign. Okay, the last piece, I want to do a quick comparison of exothermic and endothermic. And then my battery on my phone's probably going to run out, so this is theory, but I wanted you to see it all on one table because we talked about how to figure out if a reaction was exothermic or endothermic in many different ways. So let's look at those ways. So with enthalpy, if you have a negative delta H, a negative enthalpy, that means it's an exothermic reaction. If your enthalpy or your delta H is positive, it's endothermic. Now, if you're calculating heat energy, and by heat energy, I'm talking about those Q values, that calories, where you're given the mass, you're given the specific heat, and you're given the change in temperature. Okay? For these values, the Q values, if the Q value is positive, so if the change in temperature is positive, that means that the object is heating up. You can feel it getting warmer in your hand. It's exothermic. If the Q value that you calculate is negative, that means the change in temperature is negative because you can feel the object getting colder. It's endothermic. So object getting hotter, releasing heat, exothermic. Object getting colder, absorbing heat from your hand, endothermic. Now when you're looking at a reaction equation, when you have the heat as a product, it is exothermic. So if the heat shows up on the product side of the reaction, it's exothermic. And then you can guess if the heat shows up on the reactant side, it is endothermic. And last but not least, definitions. So if heat is released to the surroundings, meaning if you're holding onto that flask and you feel it get warmer, it's exothermic because it's releasing heat to the surroundings being your hands. For endothermic, then, it's absorbing heat, which means if you're holding on to it, it feels like it's getting colder because it's absorbing the heat from your hand, making your hand feel colder. Okay, so this is really going to help differentiate between exothermic and endothermic in every single possible way I believe that we've discussed, other than the reaction coordinate diagram. All right, so that is it for the review. I will be doing some optional Zoom reviews that you can join in as well, where you can ask specific questions, and we'll work through some different types of problems if no one has questions on those. So, good luck.